Hi, my name is Brandon Bloom, and today I'm going to talk about dendrology, which is the study of trees. And the title for this talk comes from Gary Fredericks, who said this to me in the Clojure IRC channel. I made an offhand remark about how I'm interested in new ways to process and analyze trees, and I'm obsessed with this idea since coming to Clojure. And Gary said, well, B. Bloom is a dendrologist. And I laughed pretty hard at this. He told ClojureBot. ClojureBot now remembers that. And it makes me chuckle every time I think about it. But I think that as computer scientists, and especially as Clojure programmers, we should all be dendrologists. We should all people who love and study trees. And so we'll talk about what I mean by that and why. First, some assumptions. You love data. You like immutability. You like values. You like these things. Right? You're Clojure programmers, you like all these great ideas that Rich and Clojure has put into your mind. And the argument I make is this implies that you like trees. And I'm going to show you why that's the case, and I'm going to help you see trees from the weird perspective I see them. So trees are everywhere in software, but the world is not necessarily tree-shaped. And I found a piece of clip art that perfectly represents this. The world is a big puddle of spaghetti here, and there's this beautiful little piece of parsley in the middle. That's your nice functional tree in this scary, not so functional spaghetti world. And so I'm going to help you untangle this by thinking about what makes a tree and the nature of it. So what's a tree anyway? This is a tree. In this case, I labeled the tree nodes here with letters. And I've got pointers from the parent nodes down to their children. And there's some ordering here. And there are many, 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 many data structures that have this general shape or feel or look to them. This is also a tree, but this is a very different type of tree. This is a case where the children point to their parents. And this is the case you have in like a relational database, for instance. You can have A could be your customer, and B, C, D could be your orders, and E, F, G could be items. And the items have order IDs, and the orders have customer IDs. This is the parents pointing to their children. This is a very different type of tree than those that we build our everyday data structures out of. I'm not talking about this type of tree today. I'm talking about this one, where the parents point to their children. That distinction there alone, a lot of people don't make, and I think it's an important one to consider. This is also a tree. This is the degenerate case of a tree. This is a list. And this is a tree. Well, not really. This is a directed acyclic graph. But I argue that this is as good as a tree, because there's a canonical traversal of this, and you just copy the nodes, and you can think of it as a tree. And so frankly, a directed acyclic graph is just an optimized tree. And that's important. There are subtleties where that's not true, and you talk about reference identity and things like that. But by and large, you can think of a directed acyclic graph as an optimized tree. This, however, is a cycle. This is not a tree. This is a graph. And this causes all sorts of problems. So here's a real tree. This is called a banyan tree. And what happens with the banyan tree is, has anybody seen a banyan tree before? OK, so this thing is huge. This is one tree. What happens is the trunk grows up, vines come down, they touch the ground, they take root, and they form new trunks. And this is one living tree. Every time you have one of these new roots, you cannot, it changes where one tree begins and one tree ends. And so even real dendrologists get this wrong. This is not a tree. This is a banyan graph. And I argue that there are this problem where dendrologists mischaracterize this as a tree happens in programs all the time, where vines take root and form new trunks and make it really hard to say where one tree begins and one tree ends. And this is true because, and so the problem is that pointer cycles are the root of all evil. And just as with the banyan tree, this is true because they're also the tail of all evil. And so I'm going to make the case that pointer cycles are just generally evil, And I'm going to show you why and help you justify that to other folks when you say that sort of crazy idea to them. So I've got my directed acyclic graph here. I've got ABCD, and I've invented some notation. This little orange arrow you can think of as an atom, right? It's the root mutable cell for this tree. And this notation that I invented here is just B, D. I want to rewrite the tree at D from the path of B into BE. If I do this, my atom moves over. I get a new tree. I get A prime, B prime, this new E, and I have the structural sharing we all know and love from all our Clojure data structures. But what happens if I have a cycle and try and do the same thing? Well, I have to copy the entire cycle. And you might be able to think, well, I can imagine a case where that's not. No, this is always true with cycles. You always have to copy the whole cycle if you have an immutable data structure or if you have an immutable cycle. And once you create a pointer cycle, you have this problem, and you lose the ability to do optimized trees. And I'll dig more into this problem in a moment. But I want to show you this. How many people have written or know have seen a system that looks like this? Everybody's hand should be up. Everyone has even implemented this. What this is your user interface code. This is anywhere where you have that parent pointer, right? And so here, this little orange arrow, that's one parent pointer. That's like component.container or something like that, right, in your application. And even though in the source code, you only have that one up pointer, that one parent pointer, that one vine, over time, in your running application, that takes root, and all those other up arrows are just the one parent pointer in your code. So at runtime, you have far more pointer cycles than you had expected from that one little pointer. And so if you wanted to rewrite G to G prime, you have to rewrite this entire tree if you wanted to maintain your immutability of it. So I'm going to go further. I'm going to argue that it's not just pointer cycles that are evil. It's that pointers are evil, just in general. And I'll show you an example of the semantic problems of pointers in this context. So here, this orange arrow here is actually not an up pointer per se. We'll call it a cross-reference. So we can imagine this graph as, for example, let's say we're working on a Word document or he's making funny faces at me. If we're working on a LaTeX document, there we go, got it. This is a cross-reference, right? And what we want to do here is we want to change some text in paragraph B and create paragraph B prime. Well, when we do that, we now have a bit of a problem because D is pointing to the old B if it's a pointer. And so what we really want to do is we don't want that to be a pointer. We want that to be kind of like a nebulous cross-reference thing. And we actually want it to point to the new B prime. And this can happen in parallel with other threads, with other processes, other functions. If I have B prime to be double prime, I have this D tracks the B. And that pointer only has meaning, or that reference only has meaning in the context of the current document. This reminds me of something, which is this slide I shamelessly stole from Rich, which is a great slide. And this is about identities and the succession of states. And so when you think about this, B is an identity, right? It's a succession of states. It's B prime, it's B double prime. And we think about identities in the context of Clojure as atoms, as refs. But in reality, we actually have more identities than these mutable, synchronized concurrency primitives. Identity is just a more general concept. And so here, in this example, we actually have two identities at play. There's the atom, or whatever variable that is. And then there's this pointer or non-pointer to B. So let's talk a little bit more about pointers and identities. And I have to apologize, because the first code I'm going to show on screen is pseudocode in C++. My apologies for this. Here is a pointer. Let's imagine that C++ did not have pointers. And let's imagine that swear word in the middle there is some syntax that actually works to make this code correct. And here is a pointer, right? We've got our our static memory that's global. We've got some pointer. It's identified by a number. We can dereference the pointer, which brings the memory and the pointer address together. We can do math on our pointer. And this is what a pointer is. But if we get rid of that pointer math, we have a more abstract thing, a reference. And this lets us do smarter stuff like garbage collection. And we get lots of power by moving the abstraction here. So this probably still should scare you a little bit now that you see memory as a global mutable variable there. You don't think about it that way, but that's really what it is. And so as functional programmers, we want to get rid of that global mutable scary thing. So we need to accomplish that magic swear word there. So we still need memory from somewhere. So one thing we could do is we could pass it in as an argument to the reference. This is kind of problematic if memory becomes immutable, because then this reference always points to the same thing. It's not a succession of values over time. So in order to get a succession of values over time, we actually want to pass memory to the deref function. Right? We want to dereference this in this piece of memory. And now let's see what that might look like in Clojure. You have ideref, right? This is the @ sign you use for your atoms or whatever. You can imagine a protocol ideref_in that dereferences an abstract identity in a context. And I can implement this reference much more succinctly than the C++ as ideref_in memory with a swear word again. And we combine memory and that address, and we're dereferencing that in that place. So an example of how you may use this is if I had a database reference, it's a table and an ID, and I implement, I forgot to mention the protocol there, but I implement deref_in as getRow in the database. I could create an instance of this. I can use it with deref_in. So here, Brandon is user 5. I dereference it in the context of the current database. And this is this idea that I just kind of was going over. I want to make the impression that identities only have meaning in a context. And the context you generally work with is all of memory. You don't actually have to do this ideref thing or ideref_in. You shouldn't. It was just sort of for illustration purposes. In reality, you're going to do something like this. You're going to just write a getUser function, right? But what's actually happening is you're dereferencing an identity in a context. And this is akin to the example we saw earlier or talked about earlier with dereferencing a cross-reference in your text document. Because that identity only has meaning in the context of the current document. You can use this here. Get user Brandon 5, right? ID 5. This is an identity, right? This is a REST API endpoint. This is an identity. This is just a vector with user 5. This is an identity. This is Brandon. And you only know that from the previous slides, the context. 5 does not mean Brandon in other contexts. But in your applications, you do this all the time, where you have pure values that represent identities, that represent successions of values. And if you think about that, it's really deeply related to atoms and refs and all those different things, and that great slide Rich put into our collective thoughts years ago. And so the point I want to make here is that context is king. And so when you go chat with folks and they say, how was the talk in the other room? You'll say, yeah, it was awesome. And then you'll say, he put the Burger King on a slide and it creeped me out. And they'll be like, the Burger King, what was the context? And you'll say, exactly. It only makes sense in context. And so hopefully that mnemonic will help you remember to think about context. So the original identity is a symbol, right? The atoms and refs of our Lisp forefathers are symbols. And so here's a piece of nonsensical Clojure code. I define a top-level X. I reference it in several places. I shadow it. And then if I compile that to Clojure script using the Clojure compiler, I get something like this. And what you'll note is that in this context, X is a var, and in this context, X is a local. And so if you if you were at the Tim's tools analyzer talk, or if you have ever hacked on the Clojure script compiler or taken a look at the source, it is a really great place to learn about and see how to do context in a Clojure way. And this symbol being resolved in context is fundamental to how compilers work. And these symbols are no different than atoms. I just want to also point out that contexts are not just about dereferencing identities. In this case, X is a statement, or it's in a statement position. In this case, it's in a tail position. And I don't actually care what thing is in that position. It could be a symbol, they could be the same, they could be different. But in one case, it's contextually going to return because it's in tail position. And that doesn't matter that these are X or not. That's a statement about the position in the tree, not about the identity in the tree. So I want to go over some examples of context unrelated to identities and give a little bit of practical advice on working with trees in Clojure. So first, here's a tree labeled in breadth-first order. And here is a representation of that tree as a vector in a kind of hiccup-ish style. I'd recommend not doing that and instead doing this and using extensible maps. You will thank me later. Do not try to be clever. Do not try to be terse. Start with a map. Use children keys. Add extra keys to the thing. Always start with an extensible map. You will thank me when you start with the first one and then get burned by the fact that you want to put extra data in and don't know where to put it. You can always add syntax later. You can always add that abbreviation on top. And in fact, that's what we already do when we write code, right? We have this nice AST backing it, again, going to the tools analyzer example. And we write S expressions in a much more terse way on top. And so syntax can be layered later. So definitely choose the second representation by default. So we're going to do some pretty simple algorithms that, and talk about them for a way you may not have talked about them or thought about them before. We're just going to annotate. We're going to start by annotating the depth of each of these nodes. So for each node, we want to assign a depth key to it and give it a value. Here's a simple recursive algorithm to do that. We kick off at the bottom there with the base case, and then recurse down the tree, incrementing the depth as we go, and then associating it into the map, and then recursing over the children. What I want to point out is depth here. This single integer is your context. And this context gets merged onto the tree. Again, recommending that this is valuable because I wanted to put the data on there. I just do this pass over the tree, and I have the benefit of the heterogeneous map. And we're passing that context through the tree downward. There are also examples where you pass context upward through the tree. So here I want to annotate the max depth. So let's take that tree already annotated and do another pass over it and do another simple recursive algorithm. And this time, we're getting the depth from the node, and we're passing it up the tree. And in this case, it's the same traversal, but we do some work when we back out of the recursion rather than when we go into the recursion. And this pattern happens all the time when you do recursive algorithms on trees. You want to think about if I have what the attribute grammar folks would call an inherited attribute that goes down or a synthesized attribute that goes up. So let's look at something that's oddly a bit trickier that you wouldn't expect, which is a depth-first numbering of the tree. Here, this is the depth-first traversal, the way the order would go. I give each node a number. It's its index. And we'll start not by numbering the tree, but by printing the tree out in numbered order. So here I got A is 0, 1, B, da, 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 da. Here is the simple recursive algorithm that does that printing. And it's exactly the same as you saw before, but this time we're threading through an index instead of a depth value. And we're kicking this guy off with the base case, and we're returning nil because we're not returning the new tree, we're just printing it. And this is very simple, and this matches the simple recursive algorithm you guys did in Algorithms 101 when you were writing C or Pascal or whatever they taught that class in, or Java nowadays. And so it turns out to be a little bit trickier when you have immutable data to number the tree and actually return the tree changed, because you want to return the tree changed and all of the other changes along with it. And so it gets a little messier, and you have this number depth-first recursive. And you'll note here that it's the same shape as we've seen with the reducing over the children. We're threading an index through and a max index as well. So the index is inherited and moving downward, and the max index is synthesized and moving upward from the children. And at this point, you're probably looking at this and going, man, I remember this being a lot easier in my algorithms class. And for some weird reason, this functional version of it's like a little bit hairier. And I think that's because you're actually seeing the actual true nature of the problem in order to accomplish this. And so you may be tempted to do this imperatively. And frankly, this is the version I would write. But I just wanted to show you what's kind of behind this, right? This is looping over it recursively and incrementing an index every time through. And in this version, I just update in the current children and recurse and update in the assoc, and I get the depth-first numbering that way. And the atom here is effectively doing the inheritance and synthesizing of that data for us. And don't feel bad to use a little bit of mutability to simplify your code here. Although there are other ways, right? And so we'll look at some. Let's look at an iterative version of printing, not numbering this tree. Here, this is an iterative version, and we're just doing a loop. And what I've done is I've made the stack, the execution stack, explicit. It turns out that whenever you traverse a tree, you have some context that you're getting for free from your evaluator, from your interpreter, from your compiler, from your runtime. You're getting the call stack. And that call stack's a data structure. And you're kind of cheating by leveraging it as part of your algorithm. And so here I've made it real. So that nodes list with the initial node is a stack. And each time through, I push the children onto that stack. And I don't recommend you use concat to build a stack that has some issues. But I did it here for a reason to illustrate something, which is that by reifying the context, by making it a real thing, something we can talk about, first of all, I can debug it now. I can print that stack out. But more importantly, I can make an observation that if I swap those two values, I switch from a depth-first traversal to a breadth-first traversal. By switching from a stack to a queue, I've changed this algorithm to do something different. If I were to have done this recursively, I would have had to totally rewrite the entire algorithm to get a breadth-first traversal. And so by making the context explicit, I was able to have this insight and this benefit. And so, sure, the recursive algorithm using a stack is convenient, and you should write the more straightforward natural code in the general case. But you need to be aware that that's what you're doing, right? You're leveraging existing context, and that has a cost. And the cost is it's harder to debug, but it's also harder to make these sorts of changes when you swap out a data structure and get a different and corresponding algorithm. So again, that's just printing the tree. If we wanted to iteratively label the tree, we can look at the context at E. And so at E, we have this queue of nodes to visit and this stack of the trees above us. And when you see a pair of stacks like this, you should be thinking functional queues. And when you're seeing functional queues or stacks in this way in a tree shape, a thought you may have is zippers. And Clojure zippers, I've regretted using almost every time I do, but I've not regretted learning about them. And so I highly recommend you play with them and get an intuition for them. And then you can do like David said in his Ohm talk and encode context of your tree in a different style than in the up, down, left, right zipper style. But I'm going to use zippers here to illustrate how you can do a functional iterative traversal with reified context pretty simply. So here I'm going to make a zipper. I've got a branch. Any node can have children. The children are stored in the children key. I can create a new node or a modified version of a node by composing children with the node, just associating it in. And I'll kick it off with a root. And here is number depth first with a zipper. So what's happening here is I'm looping, starting with index 0. I've made a zipper for the initial position, which is both my context of the tree around me and the queue for a depth-first traversal ahead of me. I ask if I'm at the end of the zipper. If I do that, I rewind the zipper back to the root. Otherwise, I just keep on I recurse through this thing iteratively, proceeding to the next location. And what's happening here is that the complete context of this algorithm is data. The index, right, that synthesized, inherited, chained attribute. The traversal context, both the future of the traversal and the past of it, and all of the tree surrounding it are encapsulated in that zipper and that index. And so I can print that out, visualize it, think about it, debug it, do backtracking, do all sorts of crazy things that I couldn't do if this was hidden in the execution context. And so what I encourage you to do, not necessarily to use zippers, but to think about, can I reify context as a first-class thing? What is my context? What does it look like? And if you think about that, you'll actually come up with more easy to debug and more easy to change programs. Now, I'm not going to talk about a breadth-first numbering, because it turns out that Clojure zipper API won't lend itself to a convenient swapping of the concat order. And there are some pretty interesting bits of research around, like, why is this surprisingly difficult? Why does that code look hairier than the imperative version? And I'm not going to try to pronounce their names, but these guys have done a lot of the work on functional data structures, on functional iterators, and this idea is now well understood in the research community. And what I encourage you to do is to try these examples on your own in a functional way, that these really simple examples from like your early 101 algorithms classes, and pay special attention to context when you do so. And you'll learn something, and you'll internalize these ideas. And then when you're done, try these. Try doing a breadth-verse iterator. It's a little bit of a mind bender, and it's kind of fun. So what I want to do is leave you with the key ideas of this talk, which are that when you work with trees, you need to carefully consider your identities and your context. These two ideas are fundamental to language, and I mean that both in the human sense and in the programming sense. To symbolic computation, they're fundamental to trees. And if you are carefully considerative of your identities and your context, you'll have easier to debug programs, you'll have more flexible programs, you'll have faster programs, they'll have features they didn't have, like backtracking iterators can give you, and all that sort of stuff, and you'll have happy trees. And the result is that you will be a dendrologist like me, and king of the mountain, and take over the trees here. And this sort of thinking has been really beneficial to me in my work in Clojure, and I hope it's beneficial to you. So thanks.